Okay, here we have a quick lesson on benzene physical properties and reactivity. And we're going to cover off naming as well. And then we're going to have a look at the reactivity, why it's less reactive than we might think. And then have a look at the combustion of benzene and benzene products. So first of all, physical properties. What physical properties do we mean? Well, the usual ones. So we're going to look at boiling points and melting points and solubility. So boiling points and solubility. Let's compare benzene to other products with similar MRs. Let's compare benzene and hexane. So benzene we're going to draw like so, and hexane we'll do the skeletal 1, 2, 3, 4, 5, 6. And so first of all, let's compare their boiling points. So boiling point of benzene is 353 Kelvin. So we're going to do it Kelvin, 353. Whereas hexane is 354. So very similar. And melting point, however, is slightly different. So melting point is higher than hexane's. So hexane is 178, whereas 279 is the melting point of benzene. Okay, let's try and explain this. Melting points, what we have to do is we've got the fixed benzene molecules, and we have to separate those benzene molecules, and they fit together quite tightly. Whereas hexane molecules, being the shape they are, fit less tightly together because these are planar, and these are non-planar. And that difference in shape explains the difference in melting points, in that the van der Waals forces are stronger with benzene because the molecules can fit together closer. In terms of the boiling points, that's more to do with the separating the molecules completely, and they're similar, as you see, because they're going to have similar van der Waals forces. Okay, so that's boiling and melting points. We can discuss solubility. They are both, of course, non-polar molecules, and so they're going to dissolve in non-polar solvents, but not polar solvents. So both soluble in non-polar solvents. Non-polar solvents. Okay, and that's about it. That's all we need to know about the physical properties of benzene. So now we can talk about naming benzene compounds. So let's draw a couple of molecules. Let's draw chlorobenzene. So you start off by drawing a benzene molecule, and that's a chlorine atom attached to it, attached to one of the carbons, and that's chlorobenzene. So that would be C6H5Cl, where one of the hydrogens has been replaced by a chlorine. And bromobenzene would be the same, with bromine instead of chlorine. We can draw nitrobenzene. So again, start off with a benzene ring, and a nitro is an NO2 group. That would be nitrobenzene. Nitrobenzene, with formula C6H5NO2. Okay, and let's do one more. Let's do methylbenzene. So again, we'll have a benzene ring, and this time a methyl group, which we know is CH3. So that would be methylbenzene. And if we wanted to, so because there's one methyl group there, we don't have to number it because all the carbons are the same. But let's say we had two methyl groups, then you would number the carbons, and which way around you number it just means that you want to do it in a way that lets you use the smallest numbers. So you would number it around this way. The carbon speed numbers like so. So this would be 1,3 dimethyl benzene. So that would be 1,3 dimethyl benzene, like so. So now we need to mention a new word. We need to mention the word phenyl. Let's write it down, phenyl. And it's closely related to the word alkyl, which you'll be very familiar with. And alkyl, we know when we start off with an alkane and we remove a hydrogen, we get an alkyl group. So for example, you would have an alkane like methane, and you would get CH3, which is methyl, which is an alkyl group. And in the same way, we can make a phenyl group. So, except we start with a benzene. Start with the benzene, remove the hydrogen, and we get a phenyl group. So let's illustrate that with some examples. We could have phenylamine. Let's write the name, phenylamine. And so we can draw that out. So you draw a benzene ring, pretty much the same as we did before. But this time we're going to have an amine group, NH2. We could draw phenylethanone. Phenylethanone, which is a ketone. So that's going to be a benzene ring again. With the ethanone attached to it, so that's going to be our carbonyl carbon, and that's going to be the rest of our ethane part to the molecule. So that's phenylethanone. Notice it's a ketone because we've got two carbons, so this is a carbon here on that junction, and of course we've got a carbon there that I've just put the arrow towards. And so having two carbons associated with the alpha carbon that's in the carbonyl group, that makes it a ketone. So there's a couple of examples where the name starts with phenyl. And I hear you asking a question, when phenyl, when benzene? And there's not a clear-cut answer to that, unfortunately. So notice that these were, a functional group followed by benzene, and these are phenyl followed by a functional group. The rule of thumb is that when the benzene functional group, Fg, when the benzene functional group is sort of more important than the other functional group, then we call it something benzene. But when the other functional group is more important than the benzene functional group, then we call it phenyl functional group. Okay, so that there is phenyl ... and this one here is ... benzene. But which functional groups take precedent over the other functional, over the benzene functional group, is just something we have to memorize. There's no fixed rule for it. So unlike most of the naming that we do, this one is just a little bit more subjective, and we're going to have to rely a bit more on memory for this one. So we're going to talk about reactivity now, the reactivity of benzene compounds. And we established in the previous video that the stability of the ring of pi electrons, the double ring of pi electrons, makes the molecule very stable and therefore unreactive. Okay, so what we can say is this: we can say the stability of the benzene means that it does not perform addition reactions like other alkenes. So you remember addition reactions like when either hydrogen or a halogen is added to a double bond. Then that happens quite readily with most alkenes, but not benzene. And benzene is a double bonded hydrocarbon, an alkene in other words, called an arene. Okay, so that doesn't happen, and the reason why that doesn't happen is because if it did happen, the delocalized ring of electrons would be broken, right? Therefore removing its stability, and it doesn't really want that to happen. So it's very difficult to make that happen. So let's talk about the benzene reaction. Here we've got the familiar benzene test for double bonds. And in the first test tube on the left, we've got the mixture of bromine water. So that's this one down here is the bromine water. The bottom layer is the bromine water. And the top layer is the benzene. And they've been mixed and separated again, and you see that the colour of the bromine water has not been discoloured. Whereas in this test tube, we've had cyclohexene. Let's do that in a different colour. So we've got cyclohexene, and this was the bromine water. So it's cyclohexene used because it's got a double bond, but it's a cyclical molecule like benzene is, but it doesn't have the delocalized rings of electrons. And that double bond that's in cyclohexene did react with the bromine molecules, and so the bromine in the water disappeared and formed a halogenoalkane, a bromoalkane, and that is clear, as you can see in the second test tube there. However, the bromine molecules weren't able to add on to the benzene molecules, weren't able to attack the double bonds in the benzene molecules, again because they are delocalized around the ring. So what we can say is that the stability of that benzene from the delocalized rings means that we don't really do addition reactions like other alkanes, but they do react. They do substitution reactions. Okay, we're going to talk about substitution reactions subsequently, but substitution reactions briefly are those reactions that swap one group for another group. So in this case, we're going to lose a hydrogen, one or more hydrogens, and replace them with a different functional group. And because of that replacement, in inverted commas, you call it a substitution reaction, or a swapping reaction, but we don't do addition reactions. So next up is this combustion statement here. The arenes, arenes is another word for aromatics. Arenes burn with a smoky flame. Here's a picture. Okay, so we've got some possibly benzene, possibly not benzene, because benzene is very toxic. It's very carcinogenic, and so in school labs it's certainly not used. But it might be methyl benzene. That's what we use in labs instead. Less toxic and not carcinogenic, so we can use that. And as you can see, when it burns with a smoky flame, and that's because the carbon to hydrogen ratio is high. So the carbon to hydrogen ratio is high, which means you get this smoky flame. In compounds like alkanes and alcohols, then you get very clear flames and very clean flames, and that's because the carbon hydrogen ratio is much lower. You've got more hydrogens and less carbons. So there you have it. That's how arenes or aromatics burn, and that brings us to the end of this little lesson.